Okay, let's go ahead and come to order. I think it is the appointed time. Let's spend just a couple of minutes going over this latest homework. Maybe I can shed a little bit of light. I've had a couple of questions. So, you know, I've cut and pasted information, and let's see how we might use some of this. So let's see. So I want you to just indicate or calculate as required. So real KW demand on peak, off peak periods. Well, on peak, off peak periods. So, you know, you have your contract demand. We have consumption. Here is your peak KW for the on-peak period, and here's your peak KW for the off-peak period. So that's pretty straightforward. Just take it off the bills for one. The maximum demand, you just compare those two and select the larger. Apparent power for on-peak and off-peak periods. Let's see, does it give you, let's see, so meter, valley, you've got kVAR. Okay, well, so you're gonna have to calculate that. That's from the power triangle. Okay, so you're given, for example, the on-peak period, you're given the KW, that's the piece of, that's the cosine portion of the triangle up on top. I have a hard time drawing this stuff. I guess, well, let me see. I guess I can do this. Okay. So let's see. Insert shapes. There we go. I'm going to have to format it. Format shape, solid line. It's always got to be hard. Okay, so let's say that's the KW portion. And let's see, we get this up here side by side maybe. Oh, Lordy. Ain't it bad? There you go. Yeah, I'm not seeing what I want. Anyway, okay, so this line would be the KW up here. Then if we come down, let me copy that. Copy, paste. There we go. So that's the kVAR side. And that's the kVA side. So if you take the kW and divide by the power factor, you get the kVA, because power factor is nothing but this side divided by this side, right? So if I take the kW and divide by the power factor, I get this side, okay? And then the kVAR is given, there's your kVAR at peak is 7802. So that's this side is the 7802. And this even tells you your power factor is 89.7. So that gives you all three sides of your power triangle, okay? kW, kVA, kVAR. And so if you use Pythagoras' theorem with this and this demand and the kVAR squared added together square root, you should get this. And if you take the kW divided by this, you should get the power factor. Okay? So, okay. So the kVA, that's the hypotenuse on peak and off peak. So just two different power triangles. Reactive power on peak and off peak, it gives you in the bill. There's kVAR on peak, kVAR off peak. Let's see, power factor percent and power factor angle in degrees. Well, so you have to, yeah.
So, you said that calculate all goes down power triangles. If you don't want us to do power triangles to, I guess, back up what it said.
Yeah, sure.
Okay.
That'd be great.
It's like that's like for like my on peak and off peak on part A. I did calculations and they were pretty damn close, but they weren't exactly what it
Well, I mean, some of this may be rounded
okay.
a little bit.
Okay. So it's okay if that's what we did. So just,
Yeah.
oh, it's that. Okay, right.
Yeah, I mean, if it's essentially the same, that's fine. Yeah.
Okay.
Okay, so I think E shouldn't be a problem. I mean, I think you're given the percents, and you just need to calculate what this angle is. So given the sides of the triangle, I would hope that's not going to cause anybody a problem. You pull that thing out. So you just, this is the power factor angle right here. So, you know, use whatever trig function you like. Dollar cost of power factor penalty paid. Well, let's see. So, okay, so reactive demand charges. And so if the reactive demand in kVAR is lagging, which it's going to be, during the 30, okay, and this is the averaging portion of it, 30-minute consecutive minute period beginning or ending on a clock hour of the month in which the consumer's highest metered demand occurs. So the penalty is tied to the highest metered demand, whichever is highest between on peak or off peak. It goes to the highest one. Shall be added to the customer's bill a reactive charge. This is the power factor penalty of $1.46 per kVAR of the amount. Am I recording? Did I start recording? Yes, okay. Okay. By which reactive demand exceeds 33% of such metered demand. So that's 33% of the kW. Now, where does that come from? Well, if you play around a little bit here with this power triangle, so let's make up some numbers here. Okay, so let's say that this piece up on top is 1,000. You can say 10,000, just make it 100,000, you know, whatever. Just say it's 1,000 just to make the numbers easy, okay? And let's say that the power factor was 95%, okay? Then the hypotenuse would be what? 1,000 divided by 0.95, okay? So 1,000 divided by 0.95 is 1,052.6. And I'll store that away, okay? Now, so I've got 1,000 on top. The hypotenuse is 1,052.63. Let's use Pythagoras' theorem and calculate the kVAR, okay? So this up here on top is 1,000. This hypotenuse is 1,052.63. That makes this little short sine side over here, squared minus 1,000 squared equals square root 328.68 store 2. Okay? And so for this 1,000 kW of demand, I am allowed 328.68 kVAR. So let me take that 328.68 and divide it by the 1,000 to get the ratio. Divided by 0.3286. 0.3286. And what's it say in the rate structure? It says take that kW times 0.33. And that's what's allowable. So see, they just rounded that to 0.33 in the rate structure. And so when you do that, that allowable kVAR is a power factor of 0.95. So they're trying to make it easy or easier for people that are out there, their customers, to understand what they're doing. So that's where that, let's see, where to put the rate sheet. So what you do is whatever your max demand is, you multiply it by 0.33, and that's what's allowable without penalty. Okay? And so then we go back up to the bill. Oops. Come on. Is that the right? I got too many files open. That's the one. There. No. Electric rate. No, that's the one. Is that not? I'll tell you, this is. Oh, there it is. Can't find it. Hallelujah, it's a miracle. All right. So this off-peak is higher. So you take 16,115 times 0.33, and that's what's allowable. Okay? And you compare it to this number, and anything that's over 33% of this number, you have to pay $1.46 for. I don't know if that makes sense to you or not. Anyway, that's the calculation. Okay, dollar cost power factor penalty, both lagging and leading. So here's your leading kVAR. And so this is the max leading. So this is, see, they don't give you one up here. So this is what you're going to have to pay for on the leading side. And they don't give you any, you don't subtract anything off of it. So you have to pay 617 times, I think, whatever that rate is. That's $1.14 per kVAR for that. I'm struggling with my Word files today. I still don't have it, do I? It's got to be this one. All right. So kVAR capacitors needed to correct to 95%. Well, so you want to reduce your reactive demand, that sine side of the power triangle, to the point that that power factor is 95%. So that side is too long, and you shorten it by adding capacitors. Savings. Yeah, that's kind of a screwy question on age. You would save, well, you would not save the leading. Well, there's a question. You may or may not save the name. It's fine. You can say you're going to save all of it. It would be it would depend on the control of the capacitors, whether you got both of them. But primarily, it's the lagging that you're trying to correct. And $80 a kVAR to install. And what would be the simple payback if all months were billed exactly like this? So you had 12 months exactly like this. Yes? I'm sorry, I can't hear you.
For the kVARs of capacitors needed to correct 95%, we do an on-peak and off-peak triangles, whichever one's higher of the two, that's the one we go with.
No, you do it on the max.
Just do it on the max.
Just do it on the max.
Okay.
And then what you get into is, again, is how much variation. How does this change? What you really would want would be 12 months data, and even some interval data where you can look and see how this changes hourly. And in fact, on this Florum stuff, this is some interval data. I was tempted to send this to you, but I didn't. I don't know that Florum would like it. But see, this is interval data. This is recorded every 30 minutes. And see, so here's your KW and here's your kVAR. So you can calculate a power factor from that. You just have to do the Pythagoras' theorem and get the KVA, which is the hypotenuse between this, and then divide this by that hypotenuse. Shoot, we can do that right here. I haven't done that yet. So equals, so what do we want? We want SQRT of this squared plus this squared close. So there's your apparent power. So this is KVA, and this is now see, these guys had capacitors all over the place. So they've already worked this problem. And so insert. So that's their power factor. Oh, what am I doing? I don't know. Anyway, so you can see they're pretty darn close here. We can minimum, let's go 0.9, maximum. There you go. That's what correction looks like. And see, they occasionally, this is during an outage for maintenance. So see, it's getting driven to 1. But that's pretty good. That's what it looks like after you fix it. Okay.
Would they still pay penalties
It's possible.
Yeah. Why wouldn't they like try to keep their
Oh,
average
it's,
like that?
I mean, it's,
97%?
when you're this close, I mean,
It's not much.
it's pretty minimal. Let me see. It's a good question. Let's look at, we can tell something. This is their utility. So if you look, well, you really can't see, because they don't adjust the demands as part of the penalty. But you can see that's their monthly power factor at the point of maximum demand. And so, yeah, they could tweak it a little bit, but I'm telling you, I mean, that's not much. That might be $1,000 a year or something. That's a pretty small amount. I mean, the ones that are getting hit are the ones that are, 75, 80, 85% if they're being held to 95% threshold. I mean, I do have the bills. We could go run. Hey, that could be your next homework assignment, to run and see how much these guys are actually paying, but I'm not going to do that to you. But I think that's going to be a real small number, because they've done a pretty darn good job. At least half of the months are 95 or above, and the others are pretty darn close. So that's pretty good right there. That's not bad. Okay, enough of this power factor stuff. So email me your spreadsheet. I mean, my idea to ask you to do this in spreadsheet is because when you change a number in a spreadsheet, it changes everything. When you do it in a piece of paper, you go up, you go, oh crud, that number's not right, and then you got to redo it. So I mean, I don't really care if you want to do it on paper, but it's really to your benefit to do this stuff in Excel, because you wind up making changes all the time, and then you change one number in Excel and bingo, everything's adjusted. At any rate. Okay, let's go on to steam systems. And let's see where we were. Ah, yes. So a week from today, you're going to have that quiz on the steam reading. Okay, so look at that. I think we talked through this whole diagram last time. Okay, anybody have any questions? All right, assuming complete understanding, we will mush on. Okay, so I think we actually even put this one up there for just a minute or two, but we're just going to make this system more complex and see how it changes. So from the previous slide, we really only have one steam pressure because we only have one header, which is right here. So I guess I would call that the high pressure header. And a header is just a distribution pipe. The boilers dump into this distribution pipe, we call it a header, and all users that want that pressure tap off of that pipe and go off to whatever piece of equipment that they're serving. Okay, so here now we have a high pressure steam header, which is taking basically the boiler pressure, and we've added 2 more boilers just to indicate the system's probably getting bigger. And we have a low pressure steam header, okay? Well, so for steam to get to the low pressure, it's all generated at the high pressure, whatever that number is, okay? Well, so how can we get steam down to this low pressure header? Well, it could pass through this turbine. This is what we call a pressure reducing valve. It could pass through the pressure reducing valve. Or, so well, this is just another turbine. We're showing this one maybe turning a generator. This could be turning a pump, an air compressor. I mean, you know, anything that is driven by a shaft can be handled with a turbine. This is a heat exchanger as before. And so we're taking condensate this is at high pressure, pretty close to the same pressure. If this is saturated steam, we're coming out of here. We're condensing it in this heat exchanger, and then the liquid falls down into this trap. When this thing gets full, this trap, by different mechanisms, will open, and that condensate will then pass down here to this tank. What's that tank all about? Anybody have any idea? What's the purpose of that tank? Okay, that's a flash tank, because that tank is tied into this low pressure header. So the pressure in this tank is the low pressure. Well, I take this liquid, this is saturated liquid, water, at the high pressure, and I'm going to drop it into this lower pressure tank. So when I do that, thermodynamically, what's going to happen to some of that water? It's going to vaporize. Some of it's going to jump into the vapor state. Let's call it, it's like a throttling process, okay? Are y'all familiar with flash steam? Is a big deal. That's what you call flash. If I take saturated liquid at 500 pounds and just put it through, just let the pressure drop through a valve to 300 pounds, instantly the temperature has to drop, right? Because if I'm saturated liquid at 500, I have to be at the saturation temperature at 500. Well, when I drop that to 300, it's still I'm gonna have some saturated liquid at 300 and some saturated vapor at 300. So I have to be at the saturation temperature at 300. Well, to make the energy balance work, the only way, I can't have all liquid on both sides, because the liquid over here at 300 doesn't have as much energy as the liquid at 500. So how does that energy balance work? Well, a little bit of it flashes into the vapor state, and then the energy balance works. Let me illustrate. I got enough stuff open. All right, this is a little steam property calculator. There's a bunch of them out there. I suggest that you get one. Now, on the test, well, the test will probably be on iLearn, and so I guess you can use whatever you want to. I can't really control that. I encourage you to be able to do it with the steam tables, but whatever. But anyway, so let's just play around a minute. Let's say we have saturated liquid, and yes, I'm going to use English units, at 500 Fahrenheit. Well, what's the enthalpy? 487.9. Oh, crap. I'm going to write this on the board. Well, I guess I could. Nah. Just a second. I got to clean up the board. Okay, so you guys at home, write this number on a piece of scratch paper. Enthalpy of saturated liquid, 500 degrees Fahrenheit, 487.9. BTUs per pound mass. Now, let's say I drop this. This is, we'll stay at liquid. I'm going to drop this to 300. Crap, that's not what I wanted. I need to do this in terms of pressure, I'm sorry. I'm going to change my number. I want to do this in terms of pressure instead of temperature. We'll note the temperatures, but what is that? 449.5. Change your number, 449.5. 449.5. So this is 500 PSI, and that's PSIA. The temperature, what's the temperature? 467. Okay. Now let's drop it to 300 pounds. And at 300 pounds, it's what, 393.9. And the temperature, 417.4 degrees F. Okay? Well, so if I take 1 pound, say, take that into a valve, 1 pound mass at 500, I'm coming out over here. And so this, so I've got 495.5 BTUs coming in. Well, golly, this stuff is only 393.9. Well, the only way is I can do an energy balance on that. Some of it has to go to the vapor. So let's look at what the vapor enthalpy is. Vapor enthalpy is 1203.3. So guess what? Enough of this stuff flashes to the vapor state to make the energy on this side the same as the energy on this side, and that's just a quality. That's just a quality like calculation of quality. Okay, so to calculate this, what we would say is 449.5 is equal to 393.9 plus X times 1203.3 minus 393.9. And that'll tell me how much flashes. Okay, so for this, let's see, 1203.3 minus 393.9 equals this store 449.5. 6.9%. So just staying. Okay. Or what's that? 0.069 pounds for every pound that comes in over here is going to jump to the vapor state at that lower pressure. Does that make sense? You might want to get on YouTube and just search for flash steam and just watch a little video. I'm sure there's some on there that will show you this liquid coming in, and all of a sudden you see vapor coming out of it, and it's because of the pressure drop. Okay. All right. But flash steam is important to us, so that's probably worth the time. Okay. So because this tank is tied to this header, it operates at this low pressure. So this liquid comes down this line, comes in here. Whatever steam is generated, just you know, what's happened is that pressure will build just slightly above in this tank as it continues to flash. And so that steam will flow into this low pressure header, which has controls on it controlling the pressure down here. Okay. So then, you know, this might be 500 pounds, this might be 300 pounds. So then this is showing what we have uses at 300 pounds. We have a heat exchanger. We have more traps. And this is showing a condensate tank, but this little arrow coming out of the top indicates that flash steam is going to atmosphere. The low pressure condensate, the flash is often taken to atmosphere as if there's much piping involved, it screws up the operation of this pump. If you try to pump a vapor and a liquid together. And so now it's possible to use this. There are several things you can do. One, you could put a vent condenser, which is just a little heat exchanger that you can run this steam through. And if you have a stream of water that you need to heat, you can put that latent energy, you can condense that steam to liquid and put that energy into that water that you're trying to heat up. That would save it. If this is a pressure vessel at all, you could take this steam and put it into your deaerator, which we'll talk about in a second. The deaerator pressure is usually between 5 pounds and 10 pounds. And so this is a very low pressure steam use, and it's a significant steam use. So this could be recovered. Now what happens is this tank is often not pressure rated, in which case if you want to take this steam to the DA, you have to replace the tank with a pressure rated vessel. Because if it's just atmospheric pressure rated, even though it would probably be okay at 5 or 10 pounds, if it's not pressure rated, you can't pressurize it. That's against the codes. And so if anything happened, oh God, you'd be sued out of existence. So you can't do it. So if it's not pressure rated and you want to use that steam at just slightly elevated, you have to replace the tank, which increases the cost of the project. So you may or may not do that. Or a vent condenser. Or there's a thermocompressor that we'll talk about a little later. You should come across thermocompressors in your reading. So I may talk about that in a minute, but I don't want to get off on that right now. This is a pressure reducing valve. So it's another way that we can take steam from this, say, 500 pound header to a 300 pound header by just drop it through a valve. However, you know, if you think about this in terms of exergy, exergy is the potential to do useful work, and you're destroying exergy by just taking 500 pound steam and dropping it to 300 pounds. You know, if you have to, you have to, but you would rather go through a turbine or something and get some useful work out of that because, you know, if you needed it all at 300 pounds, you could just generate it at 300 pounds. But obviously, in this case, we've got all of these higher pressure uses. You can't really do that. And so almost all systems, whatever the highest requirement is, that's what sets the steam pressure, and then we just drop it to lower levels for lower pressure uses. Okay, this little line indicates spray. So what happened based on your thermodynamics, if this is saturated coming into this valve, what is the overall condition? Say this is steam, saturated steam coming in here, and I drop pressure 200 pounds. What's the thermodynamic condition coming out of this valve? Superheated, right? Because what's the first law? What's the first law say about going across a throttling valve? This is the easiest one. If you do the energy balance, throw away changes in kinetic energy, which are infinitesimally small. Well, if the pipe's the same size, it's almost the same. The specific volume changes. But anyway, the basic first law says enthalpy in is equal to enthalpy out. Hn is equal to H out. So let's see. Saturated steam into a valve, say 500 psig. And we've got 300 psig out. Well, if H1 is equal to H2, well, goodness, let me see. What's a good way to look at this? Let's look at some steam tables. What the heck? Documents. Let's see, that's the temperature table. There's the pressure table. 500. Yeah, well, that's kind of what we had up there. So, well, not quite. 1205.3. Okay. Saturated steam in, 1205.3. Well, so it's got to be 1205.3 out. Well, let's see. I'm going to go in the superheat tables and see what that looks like. So we're going to say 300 pounds. Good, I have 300 pounds. So saturation enthalpy is 1203.9. I'm 1205.3. So I've got several degrees of superheat, right? I'd have to interpolate, or I can go to my calculator. Okay, we can do that. So saturation temperature is 417. Was that 417.4? Okay. So if I go to my little calculator here, I can do two-phase. No, I can do vapor, superheat. Let's see, I can do pressure, 300. And I can do enthalpy. 1205.3. Calculate. Temperature, 419.9. This is saturation. This is superheat. Wow, that's a lot of work. Does that make any difference? So I got saturated steam going into a PRV, and I've got a couple of degrees of superheat coming out at 300 pounds, from 500 to 300. Does that make any difference to anybody? Don't think? Well, okay, it depends. It can be a good thing or it can be a bad thing. If I'm coming out of that PRV going directly into a heat exchanger, does a heat exchanger want to see saturated or superheated steam? Does it matter? What kind of steam do you want to put in a heat exchanger? You want to put saturated steam into a heat exchanger because the heat transfer coefficient during the phase change is quite large. Okay? That's during the phase change. But if I put in superheated steam, I have to cool that vapor to the point of saturation before it can start condensing. The heat transfer coefficient is much lower. I might as well be cooling nitrogen or another gas. It's just a gas until it gets to saturation. Then it can start condensing. And that's where the big bang for the buck is in the heat exchanger. Okay? So, if I'm coming out of that PRV and going directly to a heat exchanger very close by, my heat exchanger may not work. If that heat exchanger was not sized for superheated vapor, it may not work very well. It may be under capacity. Now, if on the other hand, I'm going into a header system and I'm going to transmit that out a half a mile away, well, I'm going to have heat losses from the header, in which case the superheat is probably good. Because say if it's saturated and I have heat loss, then I condense and I have liquid water inside the pipe, condensate. And that's bad. That can lead to water hammer, and you know, I just don't want any more two-phase flow than I have to in my distribution headers. So it depends. So that's why that little line is there to indicate the possibility of spray. Because what you can do is you can buy these PRVs and they will spray liquid water into that steam flow to take out that superheat. So what you do is you put a temperature sensor downstream of this valve, a pretty good one, and it's looking at the temperature. And so it will control a valve and spray liquid water in here, and that liquid water will vaporize and it will cool down the flow. It will take the superheat out of it, if that's an issue. So we've got some software we'll use, and when you're speccing a PRV, a question will come up, are we spraying into the PRV? And this is the discussion. This is why you would potentially want to spray into a PRV. And the bigger the pressure drop across the PRV, the more superheat you're going to get. If you have a great big one, you could have 5 or 10 degrees of superheat. 1 or 2 is probably not enough to worry about, but 5 or 10 could drastically reduce the operation of your heat exchangers. Okay.
Dr. Cunningham. Hey,
Yes.
Doctor. Can you hear me?
Yes.
Okay. Can you explain what water hammer is a bit?
Yeah, water hammer is where little chunks of what, because of high velocity steam through these steam lines, if you get lots of water in there sitting on the bottom of the pipe and the steam is flowing at high velocity over it, it can actually entrain, you know, say there's some turbulence in the water and a little bit of it jumps up and it grabs into that flow. And that flow can be going close to sonic velocities. And you go down to an elbow or a valve and the steam makes the corner and and the water keeps going and smashes into the end of the pipe. So it's liquid water being blown at high velocity through your piping system.
Okay, thank you.
If you can keep it dry, the drier you can keep it. Now that's a reason you might want to leave the superheat in, because that gives you a little buffer. You can lose some heat before you start condensing. So I mean, it just depends. It depends on the system and the design, and what you're trying to accomplish. Good question. Good question. I would encourage everybody to get on YouTube and just look for water hammer videos. There's some really good ones out there, like 5-10 minute, and I mean it'll show you in very graphic images what water hammer can do. It can be quite damaging in a piping system. Thank you. Okay, well, so we can just continue to add more headers and more components. So I don't really see, now we've added a third header. So we have high pressure, medium pressure, low pressure, and we have all of the same stuff going on. It's just between different pressures. And I mean, you could have a component such as this turbine is operating between high pressure and low pressure. You've got a turbine here between medium pressure and low pressure. You've got in between all of these different pressures. Every time we add a pressure, when we bring the condensate down, we're going to add a flash tank. So this is high pressure condensate coming in to the medium pressure header being tied in. And so this is a flash tank serving that. And then we take liquid out of the bottom of that and put it into this flash tank, which operates to the low pressure header. This is kind of like a cascading system where we're recovering as much flash steam as we can as we drop pressure on the condensate. Then when we get it all the way down to the lowest level down here, we're showing this is vented to atmosphere, like we said before. This is a big receiver tank, and it's pumping over to the deaerator, makeup water coming in. This is our steam line that is providing the energy to strip oxygen out of this feed water, this makeup water, and return condensate before it gets pumped back to the boilers in the feed water system. So I don't know, y'all look at that, be sure and ask a question if there's something that you don't understand. I think we've been over most of it. Okay, so we're going to add one component over here. Now, this component over here, this guy is a little fundamentally different because this is a condenser. This is what the power company does. It takes high pressure steam, drops it to as low a pressure as possible, takes that steam out of the low pressure turbine, condenses it with lake water typically, and returns it back. So now an industrial plant has a hard time competing directly with the electric utility. Electric utility has bigger, more efficient, and just, I mean, that's all they do is make electricity. So if this is all the plant is doing, this portion of this operation over here can be questioned at times. If it keeps you from venting steam, if you have an imbalance in your steam system, say you don't have much high pressure, or or just, you can get imbalances in these headers that sometimes require you to vent steam. If you're doing that, then this can make sense. But just as a general comment, it's hard for an industrial company to compete directly with a utility. And that's what this guy's doing. Now, all of these other uses, say we are getting, we're getting like electrical energy out of this, and then we take it down here and condense it in this heat exchanger. That's cogeneration. That's extremely efficient. So say if you can pass this stuff through a turbine up here and then use it later in a process to condense it, you're not throwing away anything. The utility company is throwing away 40% of the energy that it took to make this, that went into the boiler to make this steam. They're throwing 40% at least away in this condenser. That's a big penalty, you know? And so the industrial guy over here, if he could get power out up here to turn an air compressor or, you know, to make electricity or something, and then at a lower pressure use the thermal energy, he is way more efficient. So that's the power in this, having these higher pressures, being able to get mechanical work in some form, and then use the steam that exits these turbines, you know, in a heat exchanger here, in a heat exchanger here, etc. And we'll talk more about that. Okay, so that's kind of my thumbnail version of this. So we're going to go through in depth and detail and talk about lots of the particulars. So we'll go through these different topics as time permits. So, you know, what are the costs associated with operating a steam system? Well, there you go. 75% is fuel. 9.5% labor. This is just average. Equipment depreciation, 9.5%. Electricity for fans and pumps. Water, sewer, chemicals. So if you're going to save money on your steam system, you're probably going to spend a lot of time looking at that fuel consumption and whatever you can do to make it smaller. So resource utilization effectively, you know, we can sometimes use different fuels. So like I tell you, paper mills are notorious. If you ever get a chance to visit a paper mill, sometimes they don't smell very good, but energy-wise, paper mills are really pretty amazing operations, a big paper mill, because they utilize waste wood, they utilize bark. When they, in the paper making process, they generate a green liquor, and they soak, it dissolves the cellulose that holds all the pulp together. They chip up the logs and put that in there. They drain that out. It's called black liquor. And that black liquor is a boiler fuel. And they burn, the primary energy source in the plant is the black liquor. They recover the ash from the black liquor. They add some more components to it, and they make green liquor again, and around it goes in a cycle. So they're burning wood, they're burning bark, they're burning waste wood, they're burning black liquor, and they're backing everything up with natural gas. They've got about at least 4 different pressure levels. They got flash vessels all over the place. And a paper mill is a good paper mill. And to be competitive these days, they have to really manage energy. A good paper mill is just a cornucopia for an energy engineer to visit and study all of their processes. It's really amazing what some of these guys do. So if you're working at a paper mill, you got to make sure that you're utilizing the free fuel first, the cheapest fuel. Is it cheaper to use green wood, bark, dried wood? I mean, how's all that work in your equipment? Because you want to minimize that natural gas. It's cheap these days, but compared to free, it still costs money. So we'll see. Distribution stuff. Okay, why do plants want to make change? What drives everything out there in the world? Bingo, dollars, money. And that's why they want to hire you, because they think they can hire you and they'll make money. They'll make more money. the more educated and better workforce they have, the better their operation will become and the more money they'll make. That's the motivation. Well, so how do you monetize in a steam system? Well, minimize energy, reliability, downtime. Things break, plant goes down, don't make any money those days. Not good. Maintenance, productivity, quality, cost avoidance, and emissions. Emissions are huge. The EPA hounding them every step of the way. And I mean, it's appropriate. We want to have clean environment, you know? Most big companies today are tremendously concerned about environmental stuff. They've gotten the message. Maybe 20 years ago, 30 years ago, sort of thing. The companies I've worked for, I mean, you know, safety is number one, environmental is number two. Energy and the stuff I want to do is number three. It frustrates the heck out of me. I want to be number two. You know, nobody gets in front of safety, you know, and it should. Got to keep people safe. But anyway, emissions, talk to them at TVA in the power industry. And efficiency is so far downstream of emissions, they will sacrifice efficiency in a heartbeat to make their emission goals or to reduce their emissions. Absolutely. That's what I've seen. Okay, so the old adage of energy management, you can't manage what you do not measure. You cannot walk up to Mr. Boiler over there and say, oh, Mr. Boiler, how are you feeling today? Now you might be able to look at the stack and say, oh, Mr. Boiler, you're putting up a lot of black smoke today. That doesn't look good. There's a few things you can see, but basically you got to have measurements before you know what's going on. All right, steam system scoping tool. So I will email y'all a copy of this. I'm not sure how readily DOE is distributing this, but this is a really nice tool. Basically, it is an Excel sheet that asks a whole bunch of questions. And it's meant for the guys that know most at the plant to give themselves a score in all of these categories. It'll give you a particular item and say, okay, this is a 5-point category. 1, you're not doing too good. 5, you're knocking the heck out of this. And you rate yourself on all of this. And the value of it is all of the different things that it suggests that people will go, man, I never thought about doing that. Oh, that's a good idea. We could do that. By the time you get through, you may have a list of 10 things that we're going to start doing that. We're going to measure that. No, we don't do that. Oh, we did that 5 years ago and we haven't done it since, you know? And all of it is good information that will let an operation become more efficient. And, you know, you get a score, but the score is just relative. It's really the thought process that's important. So there's just, you know, a typical score. So these are, we'll run through this pretty quickly. I don't know if we'll get through it today or not. But anyway, so steam system profiling, steam cost. Measure fuel cost to generate steam. Well, how well do you track your fuel cost? Does the bill come in and it goes to accounting and they pay it? And nobody even knows what we're paying? Sometimes. The guys operating the boiler, do they know what they're paying? Do they know how much you spend a month, a week, a day, an hour on operating the equipment? People need to know that stuff. A lot of places they don't. Trend fuel cost to generate steam. How is it just plotted up over time? What's natural gas cost? What's natural gas cost these days? Any idea? You can, a good thing to do, I don't have time, or I'll do it another day. You can go on the spot commodities market. like out of Chicago and the Chicago Board of Trade and all this stuff. And you can look at the spot price for natural gas, where people actually buy, big companies have people that buy futures and buy contracts going out, and they try to hedge. They try their job is to minimize the purchase price of natural gas to the company. So you can buy it from the fields on the commodity exchanges, but then you have to pay transportation to get it to your plant. And so we're seeing costs, and it's in the US, it's usually denominated in dollars per million BTUs. We're seeing numbers between $3 and $4 a million actually being charged to plants. 15 years ago, I saw numbers like 12 to $15. The price of natural gas has fallen a factor of 4 or 5 in the last several years. That's incredible. What a competitive advantage. Because we have lots of big industries that suck a lot of natural gas. I'm going to tell you what. Well, I showed you that Forum bill. What are they spending? $2.5, $3 million a year? They're spending $5 total. So they're probably spending $1.5 million, $2 million a year on natural gas. And their price is like less than $3.10. That was unheard of. 15 years ago, that would have been, instead of say $2 million, that would have been $10 million. It's incredible. And what do we have to thank for that? Why have natural gas prices fallen? Have we talked about that in here? I don't think we have. Why has natural gas gotten so cheap? Fracking. Have you heard of fracking? Hydraulic fracturing? Some people don't like it. Oklahoma, they have 2,000 earthquakes a day or something. And they blame it on hydraulic fracture. It's probably true. But they're little ones. They're not great big ones, so the cities aren't falling down. But, they do directional drilling. I'll have to email you all out some documents on fracking. Everybody needs to understand and have whatever opinion you want. But the industrial people are all for it, trust me, because it's saving them tons and tons of money. They drill down, and then they drill horizontally, and then they send charges down there. And they basically put out small explosions, and it fractures. It fractures the shale. These are in shale deposits, which contain a lot of oil and natural gas. And so that loosens up the rock and gives crevices and little cracks and fissures and all that stuff. And they put us right now, there's different techniques, but the traditional approach is to use a water solution that has chemicals in there that will loosen the petroleum from the rocks. So they pump that down, then they pump it back out, and then they're supposed to, clean up all that water, and it's a bunch of water. And then the well will flow. It'll flow petroleum and natural gas. And that is because before fracking, all of these shale deposits, which are massive, Canada, the Marcellus Shale, there's all these huge shale deposits around the US and Canada. They couldn't get the gas out. They knew it was there, but they couldn't get it out. In the old days, you just have to drill down and have a pressurized well, and you pop into that. The oil would come flying up, like in the movies. And when the oil quit coming up, then the natural gas would keep coming up. And then when it quit coming up, they were done. But now they can go back down those wells, dig down into the shale, blast it loose, and the oil and the natural gas come up. You should look into fracking. So I don't know. Is that a good idea? I don't know. Short term it is. We'll see. What else was I going to say? Oh, which country is the largest producer of oil in the world? United States. We have been for the last several years. We are now, you remember years and years ago, we used to hear how dependent we were on foreign oil and imports and all that stuff. Not anymore. We're probably a net exporter of petroleum products today, brought on by hydraulic fracturing. So interesting. When I was a kid and up through my education, you know, okay, there's a limited amount of oil, natural gas, and it's true, there is a limited amount, but it was much more limited in those days. So, well, we've already had peak oil, it's going to just decline from here, and it's going to get more expensive and all this stuff. And all of a sudden, in the last 10 years, we've had the advent of hydraulic fracturing, and now instead of all the decline down here, now it's jumped way up here, and we're producing more than anybody. You know, it's hard to read the future. Okay, let's see. Now I got a few more minutes here. Steam product benchmarks. Okay, so do you measure steam versus the amount of product? You know, pounds of steam per automobile or per widget or whatever it is the company's making. Do you trend that? Are you getting better? Are you using less? Or do you have projects that say, well, you know, if we replace that daggone thing down there that used all that steam, that thing's 30 years old. If we bought a new one, it would use about half the amount of steam, and that would reduce our operating cost. Well, so engineers look into stuff like that. And then, you know, the company has to make a decision if are they going to do it or not. Steam system measurements. Measure, record steam system critical energy parameters and intensity of measuring steam flows. So just how well do you know what your system is doing? Steam system operating practice, steam trap maintenance. We will talk a fair amount about steam trap. The steam trap is some sort of a device that allows condensate to pass, but closes off when live steam appears. When it's empty with a liquid, it shuts off the steam flow. Well, they fail. They can fail closed, in which case the condensate just floods the system. Water hammer, flooded heat exchangers. Those things usually get found pretty quick because when the heat exchanger doesn't work at all, people get really upset and you go figure out why, okay? But what if they fail open? You know, they just blow live steam through them. It's just a big steam leak. Blows into the condensate return system all the time. Well, it can sit there. So how good of a job do you do at finding your failed traps and fixing them? Water treatment. You know, if we don't do our water treatment right, we'll corrode holes in things. We'll have scale build up on the heat transfer surfaces. We'll have elevated stack temperatures because we burn the fuel, but we can't transfer the heat because we've got a layer of scale on all the heat transfer surfaces. Well, that's not good, you know? So how do we do? Do we clean boiler, fireside, water side deposit? And what that's referring to is in these boilers, you know, depending on if you have a water tube or fire tube, but you've got hot gases on one side of a tube and you got water on the other side. Well, so if you have soot and debris from the combustion process, that can build up on the fire side fouling, or you can have scale and corrosion build up on the water side. So you can have water side issues and fire side issues, or both, if you're extremely unlucky. Measuring boiler TDS, total dissolved solids. How much dissolved solid do you have in your boiler water? Because it's when those levels get too high that the scaling that come out of solution, they reach a saturation level and they plate out on your heat transfer surfaces. So how do you do? Do you measure that effectively so that you can control it? Because if you don't measure it, you can't control it. Let's see, blowdown. Okay, you should get some introduction to blowdown in your reading, but blowdown is basically draining feed water, draining boiler water out of the boiler and replacing it with makeup water in order to dilute the amount of solids, the minerals and stuff in there. So blowdown, and we'll talk more about top side blow, bottom blow, and all that sort of thing. There's different places that we take this water out of the boiler for not only that purpose, but for other purposes as well. Insulation, you know, you can take an infrared camera out and walk around the boiler house and you can see in living color, oh man, that's 500 degrees up there. That should be insulated. Is it insulated or not? Is the insulation falling off? Steam leaks. you walk around some of these places. I've been, you know, especially in the States, it's pretty good, but some of these places overseas, not so good. You walk out in a plant and you see little jets of steam coming up here and here and here and here. You go, you know, we start wondering, is that flash steam or is that a leak? You know, if it's coming out of a valve, it's probably a leak, you know. So how do they do on that? Water hammer. How often do they experience it? How damaging? Inspecting equipment. Okay, on boiler efficiency. How often do you actually formally evaluate your boiler efficiency? Flue gas, temperature, oxygen content, CO measurement. So those are the critical measurements. The flue gas loss is the main loss on a boiler. It can easily be 15 to 20% of the energy that comes in the fuel is lost up the stack. It goes to atmosphere. And so the measurement you take is, what's your final temperature? How hot is it? How much O2? That relates to the excess air in your combustion system. And CO is what you get if you're not burning your carbon-based fuel efficiently. If you're burning methane, what's the methane formula? CH4. So for every molecule of methane, you get 1 carbon and 4 hydrogen atoms, or 2 H2s. Well, the H2 burns pretty good to what? Water vapor. And the carbon is supposed to burn to CO2, which I know everybody's all upset about. But nonetheless, if you burn it properly, you get CO2. If you burn it in an absence of air or something's mixing is not good, you get CO, carbon monoxide, which one, if you breathe it, it will kill you. And 2, CO is a low-grade fuel. It still has an energy content. And so you did not release all of the chemical energy in the carbon if you burn it to CO, and that's a loss. So by using your combustion analyzer, measuring these things, you can tell, you know, how am I doing? And controlling excess air, which means you look at that O2 measurement and then you make the appropriate adjustments. Okay, we'll stop there on heat recovery equipment and we will continue on Thursday.